This is going to be another short video. It's on Dfbetas. Probably of the Dfbits, cooks, and Dfbetas, this is my favorite. I think it's my favorite because I can't even say that without laughing. I'm sorry, but I think it's my favorite because the first research that I ever did, the Dfbetas played the most important role in me looking at the influence of particular cases on my results. So that's why it's special to me. Okay, so insert Darbro is a geek. All right, gang. One thing I want to show you. I meant to share this with you before. This has nothing to do with Dfbetas directly, but it does with calculating the diagonal elements of the hat matrix. So guys, remember, we've been pretty consistent throughout all of these. Well, guys, I promise you I can spell. That the hat matrix has been capital H, and H sub I equals the diagonal element in the ith position, the ith row in the ith column of the hat matrix. Well, guys, there's a way that you can actually calculate H sub I without actually calculating the hat matrix. It's really not going to save you much time, but I just thought I would show this to you before we get into Dfbetas. If it's not something you want to see, then I'm sorry. Okay. I'm going to try to write a little better. I think in the last couple of videos I've noticed I'm not writing as clearly, and I don't like that, so I'm going to try to put a little bit more emphasis on being neater, which I would appreciate if you guys would do that on your homework assignments as well. So guys, I don't know where that came from because for the most part you guys are neat on your homework assignments. All right, guys, so anyway, that's a way that you could oh goodness. These videos today have been nothing but distractions. Well, okay, dog is actually absolutely going insane. Now, guys, in this, the X transpose X inverse that you see in the middle, you know, there's nothing new there. All the X sub I it's just the observations at the ith case. So, you know, if, for example, we have I equal 1, 2, 3, and 4, and we have X sub I1 as 3, 6, 9, 11, and X sub I2 is 8, 14, 20, and 16, and then we have our Y's, whatever they may be. Then X sub 3, for example, and I'm going to concentrate on this one, and then of course the transpose of that will be obvious, is going to be equal to the 1 for the intercept, and then we're just going to concentrate on in this case the third observation, which would be 9, 20. And guys, obviously X transpose 3, just so there's no misunderstanding. It's always frustrating as a professor when a student says, "You didn't show me that." Well, some of this stuff you're expected to figure out on your own, especially at the graduate level. But you know, some of this stuff I need to show you. All right, gang, enough of that. Let's think about where we've been. And I'm going to present this kind of as a question-answer. Although that's kind of the weird thing about a video, you can't provide an answer. Tell me what you know about Dfbetas. Now, kind of rhetorical, because, you know, again, for the obvious reasons, but Dfbetas, what is it? What does it do? So I'm this very, very, very clumsy silence is giving you the opportunity to think about it. Guys, Dfbetas gives us the influence of a case I on one fitted value the y sub I. Cook's distance, what is that? Well, that's the influence of the ith case on all of the fitted values. More specifically, it looks at the sum of all the fitted values and looks at the difference of those fitted values for each case when case I is in the model and when it's actually deleted. So guys, enter into what we call Dfbetas. And again, this is probably my favorite of the three because I think it's the most influential, and it was something that really pointed something out important to me in some research. So what this df beta does, as you might expect, it's got betas in there. So this actually focuses more on the regression coefficients, beta 0, beta 1, beta 2, beta 3, and so on and so forth, than it does on the predicted values. And obviously those are all intertwined. So what this does, this being the df betas, is it examines the influence of the ith case on each of the estimated regression coefficients beta 0, beta 1, beta 2, and so on and so forth, however many of predictors that we have. And again, examines the influence of the ith case on each of the estimated regression coefficients when I is deleted. So we remove the ith case and we look at how it affected B0, B1, B2 as compared to when it was included in the model. Okay. Now the notation here is a little different, and so the df beta which is denoted B sub ki, where k is the predictor variable coefficient, and I case that we actually delete. Okay, so the calculation for this is equal to the beta that we get from running our initial model minus the beta that we get by deleting the ith case over the square root of the mean square error with the case deleted times what's called CKK. Now, this is not to be confused with, although it kind of reminds you with HII. Big difference is HII pertains to cases. CKK pertains to variables. Okay, more distractions. Wouldn't expect it any other way today. All right. I'll tell you what, this is my wife, and let me make sure. I've got a sick daughter, and I just got a text from her principal. So let's see what's going on about this. All right, guys, I'll tell you what, I'm going to try to go ahead and get through this video, but I don't know if it's going to happen or not, because it looks like I may be going to school to get my daughter. All right, so let's go on through this, okay? Now, what CKK is, this is the kth diagonal element of X transpose X inverse. And guys, remember, X transpose X inverse comes from the variables, not the cases. It comes from, well, actually it comes from a little bit of both, I guess, if you really think about that. All right, guys, let's try to put this together. Recall that the variance covariance matrix for our betas from many moons ago starts out by looking at the variance of our beta vector, and this was the variance of X transpose X inverse. Guys, we should know that by now. So the variance of one particular beta, let's call it beta sub k, is the variance times the diagonal of that particular matrix, that product matrix. Actually, the inverse of the product of the transpose and X. Keep in mind that this is estimated by the mean square error. And since we're examining the omission of the ith case, we end up with the mean square error sub I. All right? Guys, df betas at the end of the day have two parts. First thing that they have is a sign, either plus or minus. And what the plus or minus indicates to us is whether the inclusion of the ith case leads to an increase or decrease in our beta coefficient and our estimated regression coefficients. So let me write that down. Now this tells us whether the inclusion of the ith case leads to an increase, obviously that would be positive, or a decrease of beta sub k. Now obviously the other thing that we look at is we look at the magnitude. So if we can think of the absolute value of the df beta, looks at the magnitude, and that just tells us in terms of standard deviations the difference in the b sub k's. Well, not the b sub k, but the b sub k with I in our model and b sub k without our I in the model. Now, where's the drawing line here? Well, if we have a small to medium n, it turns out if the absolute value of the df betas are greater than 1, then we have reason for concern. If we have a large n, then the absolute value of the Dfbetas must be bigger than 2 over the square root of n. So let's I'll tell you what, let's work an example. I didn't really know whether to split this. I actually kind of worried about it. I guess whether or not to include Cooks and Dfbetas. But I guess if that's all I've got to worry about, then I guess my life is pretty darn good, right? So what I'd like to do is I'd like to calculate. So I want to demonstrate the calculation of df beta for the first variable, eliminating the third case. And what I want to do is I want to do this on body fat predicted by triceps plus thigh. Okay? And so guys, from our formula, we know that we need for df beta for the first. So guys, this is our first variable. This is our second variable. So our attention here is on triceps. How does the beta, the estimated regression coefficient for triceps, change when we have the third case in our model and the third case not in our model? So guys, this is going to be what? It's going to be the beta sub 1 minus beta sub 1 with the third case deleted over the square root of the mean square error with the third case deleted times C11. Now, it's so tempted to put C33 because we're so used to concentrating on the case, but we put the 1 because it's the first predictor that we want to examine the change in. Okay, so let's run through this. I think this is going to be worth running through. No, an R. I've got R up and running. Oh darn! Seems like I never have anything going when I. Darn it! Darn it! Darn it! I don't know why I'm doing names, because I should know this thing like the back of my hand. So guys, let's go back over, and again, let's just think this through. What I need is I need B sub 1. I need B sub 1 when the third case is deleted. I need my mean square error when the third case is deleted, and I need my first diagonal, well actually it's going to be my second diagonal element on X transpose X inverse. All right, so guys, let's make it happen. Well, I just got to do the same old stuff. It kind of gets old. Okay. And I'm going to do these calculations the quicker way, just using the LM command and things. But I need this for the C11 component. So guys, what I need here is I need solve transpose of x times x. And when I examine, let's see, so this is the one I need right here, isn't it? Yeah. Okay. Because this would be the variance for beta 0. This is the variance for beta 1, and this is the variance for beta 2. So guys, C11 is 0.0142. Okay, now let's go ahead and run our model, and I'm going to cheat here. Not really cheat, I don't guess. So guys, with everything in, the estimated coefficient for triceps is 0.2224. Now everything else I need to do is going to require me to delete the third case. So what I've got to do now is I've got to create some new data, just like I did in a previous video. And what I want to do is I want to subtract out the third right? But I want to keep all the variables. Yeah. That's not the way that works. I didn't think that was it. I want data, brackets, minus C3, comma, space, and now this is going to work. Now I got to attach my new data. And I always like, when I do something like this, I always like to check it out. And notice we have, it looks like we have 20 observations, but we only have 19, because you can see right here that the third case has been deleted. Now, what I need to do now is I need to run a new model. And I want to do this on body fat, predicted by triceps plus thigh, okay? Now, summary of my new model is going to give me what I need. All right, gang. No, it won't. It gives me just part of what I need. So the change in the estimated regression coefficient for triceps, well, I don't know the change yet, but the new value is 0.5641. So, guys, that's going to be beta 1 sub 3. And then I need to run my mean square error for this model. So, guys, we should know that the way we do that. So the mean square error for the new model is 5.87. All right. Now I'm going to go back and make some calculations here. So, guys, our df beta. For the first predictor variable with the third case deleted is going to be 0.224 minus 0.5641 over the square root of the mean square error, which is 5.87 times 0.0142. And I'm going to grab my calculator. All right, so 5.87 times 0.0142. All right, guys, it looks like our df beta for the first predictor variable when the third case is deleted is negative 0.118. And that tells me that the predicted value, or I'm sorry, the estimated coefficient is about 1.18 standard deviations below what it was when I equal 3 was included in our model. Now, more importantly, to actually put this in its proper context, what I want to do is I want to take the absolute value of 1.18, which negative 1.18, I'm speaking ahead. And guys, this is what is probably most important to me now, because we have a small data set, n is equal to 20. So it is greater than 1, but it's not a lot greater than 1 to where I would lose my mind and think that I've got major issues here. So, guys, I'd want to examine the dfbetas for all the cases and all of the variables, and keeping in mind the threshold is equal to 1. All right, gang. That's the end of this video, and so it looks like what's going to happen here. The reason I'm ending it is I want to find out what's up with my daughter and find out whether I have to go pick her up. So that's why I'm ending this one here. I've actually got more stuff I want to teach, but I can put that up in a later video. So, guys, take care.